All right, so we're going to continue with 13.6 by looking at the second half of the lesson, which is on proving identities. So we're going to take all the fundamental identities that we talked about in the last class, and we're going to apply them to proving identities now. Okay, so first off, we're going to look at general strategies for proving identities. There are two. One is to simplify the more complicated side until it is identical to the other side. Okay, that goes anytime you're proving identities. So if you have two sides, which you will always have two sides when you're proving, okay, you'll have a right side and a left side, you will always pick the more complicated side to start with. The second strategy is transform both sides of the identity into the same expression. So transforming both sides of the identity into the same expression means you can start on one side, work your way to halfway point, start on the other side, work to the same halfway point, and then they're equal to each other, okay? They are not saying, however, that you can work across the equal sign. This is wrong, okay? If at any time you find yourself working across the equal sign, you are doing it wrong. Got it? So that's important to keep in mind. Now, general strategies are what we're going to look at every single time we're proving. Special strategies, however, apply to each one individually as you go through. Okay, sometimes you'll use more than one, sometimes you'll use just one, sometimes you'll use none of them. It just depends. So, first one, express functions in terms of sines and cosines. All right, so if you're stuck, best bet, transform everything into sines and cosines using your knowledge of identities. Second, look for expressions to which Pythagorean identities can be applied. So that's sine squared x, cosine squared x, those ones, okay, from the last lesson. Third, use factoring. Factoring's your best friend sometimes, okay? So keep that in mind. If you see something you can factor, try and factor it. 4, combine terms on each side of the identity into a single fraction. So, combine, so get common denominators, that kind of thing. Multiply one side of the equation by an expression equal to 1. Okay, so you can multiply by sine x over sine x, or more commonly, what you'll see is multiplying by the conjugate. Either one works, all right? But you have to make sure you're doing it as an expression equal to 1, otherwise you cannot do it. So let's go ahead and look at some examples. We'll start off by looking at number 32. Okay, it says sine squared alpha times cosine squared alpha plus secant squared alpha is equal to secant squared alpha. So we have our left-hand side, it's right here, and our right-hand side. And we need to work our way to one side or the other by getting the identity the same on both sides. So I'm going to start with the left-hand side. So I'm going to copy that back down. And the reason why I'm going to start with the left-hand side is because it's the more complicated side. From here, I want to figure out a way to get to the right-hand side. So what I'm first going to do is change everything to sines and cosines. So I already have sine squared theta alpha on the outside, so I'm just going to copy that. But on the inside, I've got cosecant squared alpha, which is 1 over sine squared alpha, plus secant squared alpha, which is 1 over cosine squared alpha. Okay. Then I'm going to get a common denominator inside the parentheses. So this will be cosine squared alpha plus sine squared alpha over sine squared alpha cosine squared alpha. Okay. Cosine squared alpha plus sine squared alpha is a Pythagorean identity. So this is going to be equal to sine squared alpha times 1 over sine squared alpha cosine squared alpha. My sine squareds cancel, and I'm left with 1 over cosine squared alpha, which is equivalent to secant squared alpha. This is my right-hand side. I've made them equal to each other, so therefore I am done with my proof. Now that little square just means that my proof is done. I don't need to move any further. That's just for me. You don't need to say that, okay? But do notice, all of the work for this, your answer is all of that part. Okay, it's great that you got to the other side, but I need to see all of this work here in order to earn any points on these. Otherwise, I might as well just have you write down the equation 3 times. Yeah? For 38, cosine squared theta tangent squared theta plus sine squared theta, tangent squared theta plus 1 is equal to secant squared theta. Again, the left-hand side is obviously the more complicated one, so I'm going to start with my left-hand side. Okay, now looking at this, you may be tempted, well, I've got two tangents, and then I've got sine and cosine. They don't literally look the same. I'm going to change everything to sines and cosines. Before you go there, however, notice that in the first two terms of this expression, they both have tangent squared, right? So we're going to factor out a tangent squared theta, because factoring is our friend. Okay, so we're left with cosine squared theta plus sine squared theta plus 1. This is important. Cosine squared theta plus sine squared theta is equal to 1 by the Pythagorean identity. So I actually end up with tangent squared theta times 1 plus 1. So that was much easier. The factoring way was much easier than switching everything to cosines and sines and ending with a whole bunch of fractions. So then I end up with tangent squared theta plus 1, which is a Pythagorean identity, and it is equal to secant squared theta, which is my right-hand side. So I'm done. Okay? Now, what's nice about proving identity is that there's more than one way to prove the same identity. So, for 32 and 38, you could have done them both the ways that I did them, or you could do them differently. There is no wrong way to approach a proof, as long as you get to the other side without doing anything that doesn't fit into the laws of mathematics. So if you decide to break a denominator, that's not okay. If you do not multiply by 1 when you're multiplying something in, or anything like that. So as long as you follow the rules, you can do it the way that works best for your mind. But if you break the rules, then it's wrong, okay? So let's look at two more examples. We've got, for 54, secant y minus tangent y over 1 minus sine y is equal to secant y. So I notice that the left side, again, is a more complicated side, so I'm going to start with the left side. If you notice, all the ones we've done so far, they've always started with the left side. That is not always the case, okay? If you look in the notes, I did do one that doesn't start on the left side, so do keep that in mind. So now I want to get this left side over to the right side somehow. So first thing I notice is that I've got two expressions on the top and bottom. Neither of them are very similar at all. So I'm going to switch everything to sines and cosines. So that means I get 1 over cosine y minus 1 over sine y. Sorry, not 1 over sine y. Cosine over sine y. Sine over cosine y. Oh, geez, can't talk tonight. 1 over 1 minus sine y. I already have a common denominator in the numerator, so I'm just going to combine into a single fraction. Okay. This is then equal to 1 minus sine y over cosine y times 1 minus sine y. All right. Now I notice that my denominator and numerator are the same. Well, I have a common expression in each, 1 minus sine y. So I'm going to cross those out, and I get 1 over cosine y. This is equal to secant y. And I'm done. Okay. Now, if you notice, the one I did in the notes was a little bit more complicated. So again, like I said, there are two different ways to do everything. The one in the notes, all I did was multiply by the conjugate rather than changing everything to sines and cosines right away. Okay? Then let's look at 56. It says secant theta minus 1 over tangent theta is equal to tangent theta over secant theta plus 1. Now, we can start from either side. I decided to start from the left side just because I wanted to. You can start from the right side if you so decide. So, starting with the left-hand side, you've got secant theta minus 1 over tangent theta. I could immediately go into changing everything to sines and cosines and then go from there. But instead, I'm going to try and make a Pythagorean identity happen, because with Pythagorean, what's nice is that secant and tangent pair up, cosecant and cotangent pair up, and sine and cosine pair up. So if you're given a problem where you need to prove the identity and you have one of those pairs together, you want to try and keep them together the way they are. So what I'm going to do is I'm going to multiply the top and bottom by secant theta plus 1, which is the conjugate of the numerator. Okay? By doing that, I get secant squared theta minus 1 over tangent theta times secant theta plus 1. Secant squared theta is minus 1 is a Pythagorean identity, which is equivalent to tangent squared theta over tangent theta times secant theta plus 1. So what's nice is that by trying to keep it as it is in Pythagorean and utilizing that Pythagorean theorem, I actually made this a lot shorter of a proof than I would have if I changed everything to sines and cosines right away. So tangent theta and tangent squared theta cancel out. So I'm left with tangent theta over secant theta plus 1, which is my right-hand side. So I've made it to the end. And that's it. So that's proving identities. Again, this is really kind of, I know a lot of you are going to be wondering, well, how do I know how to start on each side? A lot of this is checking and making sure that you're really following the guidelines that are given to you on the first slide. Okay. But that's why I didn't assign that many problems on it. So the classwork is do the 4th for F block and the 5th for C block. It's page 640, numbers 31 to 37 odd, and 49 to 55 odd. And do not forget that test 20 will be on next Monday. For those of you not taking AP Bio, all right. Also on Wednesday, we'll be doing the Algebra 2 preparedness test that we took at the beginning of the year. So it's very important you do not miss that. All right, and I'll see you guys tomorrow.